high-alpha Fischer-Tropsch synthesis over the potassium promoted catalyst. Before I show you the results of this work, I'll give a brief description of the reaction systems and the catalyst preparation. This is the flow diagram of the reaction systems. Actually, we use the CSTR, as shown here. We use the simulated syngas system from syngas from CO, from pure CO and hydrogen here, and mixing in this vessel. The sample is from the vapor phase, as shown here, and the wax from the bulk phase right after the filter here. This will give you a more clear picture of the sample collection system. The wax sample was from the liquid bulk phase through the filter, as the wax filter. Then the liquid wax and water, and oil and water from the vapor phase here. Then we took the incondensable gas vapor phase to the GC, and to get the gas analyzed with the GCs. Reaction conditions. The catalyst oil was prepared from iron nitrate and as tetraethyl orthosilicate and ammonia water. Then we used the promoter of copper and potassium here. The copper is from copper nitrate and the potassium from potassium carbonate. The in situ activation of the catalyst was carried at 270 degrees C, and instead of the reaction temperature of 230 degrees C. And the pressure is 1.3 as 12 atmosphere. Space velocity 24 standard liter per hour for 24 hours. We use the 30 oil as a study medium. The actual Fischer-Tropsch synthesis conditions as follows: 230 degrees C and 12 atmosphere was a gas composition of hydrogen to CO 0.67. This slide shows you the influence of potassium contents on the CO conversion here. As you can see, from when potassium contents increase from 0.7, that's 2%. It's 5, 7.5, and 10. The CO conversion just increased from almost 14 to 40. And stabilized there. So I say below 5% here, the CO conversion increased pretty obviously. They just stabilized here. When the potassium contents, beyond the percentage of 5 here. Yeah, for Fischer-Tropsch synthesis, we always use the alpha value to measure the chain length of the hydrocarbon products. As you can see here, when potassium contents increased, was added from 0% to is 1.44. Then up to 5%, the alpha value increased from 7 very quickly to 0.9. Then beyond that point, it's 5%. The alpha value just stabilized there, just similar to the zero conversion. In this study, we used 3 potassium constants as 5%, 70.5%, and 10% here. There's it's shown here as the first line, 5%, 7.5%, and 10%. So you can see here, the stabilized conversion as hydrogen conversion is all here, like it's only like 40% here. But as the potassium content increased, the induction period that increased from it's around like 80 hours to 100 hours and to 120 hours here. So we can say the higher the potassium content, the longer the induction period. Let's take another look at the CO conversion here. Yeah, these 3 lines show the similar results to that hydrogen conversion. This line, we just add more low alpha catalyst CO conversion here. Yeah, as I showed, the conversion versus the potassium content in the slides. When the potassium content is below like 5%, the CO conversion just increases very obviously. It's like here. The stabilized CO conversion is only 26% here. Then when the potassium contents increase to 5% and beyond, then the stabilized conversion, CO conversion, goes to 40% around. Then similarly to that H2 conversion, the higher the potassium content, the longer the induction period. Yeah, it's similar to that hydrogen conversion. Yeah, it increased from like 80 hours, 100 hours to 120 hours. This one shows the temperature jump from 230 to 250. It shows you that a 20-degree temperature increase, it results in a new induction period. It jumps to, for example, the start line is the CO conversion. Sorry, it's the H2 conversion. It jumped from like a 38% to 48%, and the CO, yeah, from 30% to almost 52% here. This table shows you the effect of potassium contents on the selectivity here. Hydrogen carbon rate is not affected by the contents of potassium. Beyond 5%. This line shows you the potassium contents effect on the water gas shift reactions. As you can see here, I use Kp as a definition here. Yeah, it seems the highest Kp value here is at the middle point of that 5 to 10%. Then all the other data shows you the contents of potassium. Yeah, did not affect the selectivity of C2 to C4 and even CO2 and the methane. Yeah, only a slight increase and imaging selectivity is observed here. This was shows you the CO selectivity. It's very similar to that CO as CO conversion. That means it shows the induction period for the CO selectivity here. It jumps from very low, like I would say, like probably from 10% to a peak point 42%, then to a stabilized 40% or 39%. Then we try to understand what's going on during that induction period. So we use the multiple analysis. This one shows from our previous work. It shows you during the activation period, the phase of the catalyst change from 0% of carbon carbides, iron carbides, to almost like 90% or even higher during the 24 hour reduction period. Then there's the oxide, iron oxide. It just dropped from 100% to less than 10% during the reduction period of 24 hours. This shows you the multiple results during the, I'll say, 140 hours Fischer-Tropsch synthesis period. The carbides dropped, obviously from like 90% to 6%, then stabilized it. Then that's the iron oxide. It just increased from 10% to 40%, or like a 38, 36, 35% stabilized state. This table shows you for unpromoted iron catalyst, the carbides dropped during the Fischer-Tropsch synthesis from 23 hours, from 83% to 42% during the first 160 hours of reaction. Then the magnetite increased from 70% to 58, then 100% to 450 hours reaction. That's for unpromoted catalyst. Then for promoted catalyst, that's high off catalyst, that's 10% of potassium. Yeah, we took the sample during this time period, 21 hours, 51 hours, then 91 hours to 120 hours almost. Yeah, try to understand what's going on here during the induction period. The results show there's the iron carbides, the bulk phase iron carbides, keep it very stable between before like 100 hours of reaction here. It almost like 100%. Then started to decrease after 100 hours here. So that means the higher the potassium contents, the longer the iron carbides starting to drop. that's the actual data from the multiple results, analysis results. That's the, what's that? Now that's the 21 hours. We get almost 100% carbides, all kinds of carbides. That's 51 hours reaction. That's still we get 100% of carbides here. That's 91 hours reaction. Still, the carbide stabilized there, like almost 100% here. The only after 120 hours reaction, we start get the magnetized here. It's around like 7% here, still very low. Yeah, that's the sample spectrum from multiple analysis. That's the first sample we took from like 2 hours after reaction. Summaries. Yeah, so we can see here, when the potassium content increased from 0 to 5%, the alpha value increased from 0.7 to 0.91 and then stabilized. Then when the potassium content increased from 5 to 10%, the alpha value did not change much. Also, the night fractions of the product, hydrocarbon products, it dropped by like almost half, almost 50% here. Then the gasoline fraction dropped, just slightly below 50%. And the steel conversion, it increased from 40% to 40% when the potassium content increased from 0 to 5%. With a higher potassium content from 5 to 10%. Yeah, the conversion did not change. It stabilized at 40%. Also, the CO2 selectivity and this methane selectivity, the olefin ratios, just stabilized beyond the 5% potassium content. Yeah, also we can see from this study, the higher potassium content will get a longer induction period. In other words, we need more time to get stabilize the CO conversion to hydrogen conversion. Then an increase in temperature can result in a new induction period. From multiple results, we can see both phase of the ion catalyst did not change during the induction period. That's probably the surface composition or probably the surface carbon deposition cause that change in conversion, in CO conversion. Okay, as everybody does have to acknowledge the funding from DOE and from US DOE and the Kentucky DOE and the multiple sample done by Dr. Hansai, MD, Wichita State University. And also I want to thank the help from all my colleagues and my boss, Dr. Davis. Okay, that concludes my talk here.
How does it chemically change the catalyst? How does it modify the behavior of the catalyst to make it less prone to formation of the oxide?
I would say I don't know, I just mentioned the higher the potassium contents just stabilize the iron carbides. So we get a longer.
You know how it does that? How is that?
Oh, we don't know. We don't have any info on that.
So it is it a chemical compound, or is it just there as the potassium itself?
Yeah, some of the other research say the potassium side just stay on the top of the say like carbon deposits. I'm not sure.
Okay.
I just get that from the literature.
First, Steve.
Yeah, just a question, kind of following what Pat's question was, did you get a chance to study some type of anion effect? I noticed that you started with potassium carbonate, and then you talked about it turning into the potassium oxide. Did you get a chance to look at, say, the effect of potassium hydroxide or potassium nitrate or some other type of anion rather than the carbonate?
No.
Given that you have silica in the system, you have the possibility of forming iron silicates, potassium silicates, potassium iron silicates. Do you know anything about the state of either the iron relative to the silica or the potassium relative to the silica at the end of your reaction?
Not for this system. Some of my colleagues just do the copper catalyst.
Yeah, what about
I
that?
don't know why. We don't have such work.
Well, can you draw any analogies with cobalt?
No, because we